Hi there. Good morning, good evening to all of you from different parts of the world. My name is Edureka and I'll be taking this webinar on logistic regression. Alongside logistic regression, we'll also cover a few basic concepts on R and what is data mining and machine learning, what is the data life cycle in a machine learning paradigm, and how exactly do we productionize a machine learning system. Okay, so let's start. So basically this particular webinar is going to focus on how data science is changing the behavior of industry. Second, what is a data science project life cycle in a production environment? And thirdly, the tools and the algorithms that constitutes this new environment called data sciences. And we're going to pick up one algorithm and we'll see how exactly do we implement it with a real life case study. Okay, so here we go. So objectives of this session would be that after the session you should be knowing what is data mining, stages of data mining, what is R, what is data sciences, what is needed of a data scientist, roles and responsibilities of a data scientist, and last but by no means the least, the logistic regression exercise. So the actual exercise that we're going to do today is going to focus on logistic or logit regression. So data science applications, wine recommendation. Well, in specifically in France and in the northern coast, the eastern coast of North America, you'll find there are a lot of people who have a career which relates to wine testing. And those wine testers are really highly paid guys. So they taste and they'll figure out if the taste of wine is good or bad. But based on that, they also tell us what kind of people would like that kind of wine. So data science is helping figure out who are the set of people who would like a particular taste of wine. And let's say if I like a wine of quality X, what are the chances that I'll also like the wine of quality or taste Y? And thereby making a recommendation engine which helps in figuring out what to be served to whom. Well, we also use data science to predict accidents. Can we actually do that? Is there a real causality or a correlation that can help us predict accidents? Well, the answer is a yes. We can do that, and that is exactly the exercise we're going to do today using logistic regression. So just wait for that. Stages of analytics and data mining. So basically in a production environment, there are few stages that you need to be very careful about. Now this is not a pretty much similar to a software development life cycle. Well, the idea is same. The idea is, you test something and you evaluate it and then you finally productionize it. But the stages are different. So one stage which is really important is data understanding. So for example, the case that I was discussing with you on the accidents prediction, we actually need some kind of a domain knowledge also to understand, can that really be a possibility to predict? Well, in scenarios like epidemiology or algorithmic trading, where you can figure out if a particular stock is going to go up or down in 0.1 seconds, then you can do, or you can sneak out some arbitrage in that particular trading. So domain experience or the data understanding part is really crucial, because if you don't know what exactly is lying under the hood, then you cannot figure out how we can use that data. Now think of an example where you are supposed to figure out that offer that you're giving to a particular person, will he redeem that offer or not? Then you need to know what are the habits of the purchase habits of that person. Then you also should know what domain puts in where. So basically, do you know the retail supply of the retail supply chain of a particular product? Do you know the inventory of that particular product? Do you know the market of that product? Do you also know the customer segmentation for that product? All these questions can be answered by someone who comes in with the domain experience on that particular domain, and thereby gives us the understanding of the data. The next is data preparation. Now, we already have the data, then why the hell do we need to have a data preparation? Well, a data preparation is something like where you figure out the hidden data points. Now, think of it, think of the same example I just gave, where you need to figure out whether a particular person will accept an offer or not. And let's say you were given the entire history of his purchases in the last 1 year. So let's say you have an offer on a soap. Then figure out how many brands rather for soaps has this person bought in last 1 year. Now that's a different column altogether. Now getting that column can help us figure out if this person is brand savvy or not. So basically, using the same data set, you figure out some more attributes about that person. That is called as data preparation. Plus, cleaning the data is also part of data preparation exercise. Also, putting data into different forms. You have to change something into a number or something into a character. So all that data cleansing and data massaging part happens in this data preparation stage. Then comes the stage of modeling. Now, what is modeling? Well, and why the hell in the world do we call it a modeling step? So basically what we do is we create analytical models, which are nothing but state-of-the-art algorithms that are known in the industry of data sciences. So algorithms could range from big complex neural networks to as simple as linear regression, and all these algorithm constitutes, the algorithm that you put on a data, it could be a mixture of multiple models, multiple algorithms that will form something as a model, and that model is something you can use for doing some prediction, doing some recommendation, doing some target analysis. And once you have the data model prepared, you test it or you evaluate it. So basically, you test it on the data set you've not seen so far, and then you evaluate the predictions of the model with the actual values of the column that you're trying to predict on in the evaluation stage. If everything is fine, you go to the deployment stage. If your evaluation criteria is not meeting up to the expectation, then either there's a problem with your model, or there's a problem with your data preparation, or you've not got the business understanding part correctly. So you go back to business understanding again and see if it's not making sense with the output that you have gone from this entire exercise. If everything's fine, we go to the deployment stage. Well, the components of data science. By the way, in case you've got any questions, we'll have a session post, I complete all my stuff just for the Q&A. So if you've got the question, just write it down and I'll take it after the class. So there are 5 very basic, and I would say it's not, in fact, the components, rather the pillars. If you miss out on one, you actually miss out on the rest 4. So we can start with data engineering. Now, what is data engineering? It could be, is it something similar to what we've been doing in the ETL or the extract, transform, load paradigm, or something similar to the BI, the business intelligence? Well, somewhat. And that is because we still treat the data the way we've been treating it, just that we massage it in a different fashion. We might not put into facts and dimensions. We rather put it into the format we want to, we want to run on. Then there is advanced computing. Well, I am sure you guys have heard of something called as Hadoop, which is currently the most popular framework for advanced computing. Rather, it's not advanced computing. To be honest, it's more precisely parallel computing. So parallel computing is like when you've got a task, you divide it into parallel runnable modules, and you put it on something like Hadoop or Spark, which is the new buzzword in the market, and do some really advanced computations which were not possible previously, or they used to take a lot of time. The third part is statistics. So statistics plays more than an important role. I think it's the heartbeat of analytics. It's the heartbeat of data science. Everything that we do relates to statistics. So if I say algorithm, I don't really mean the algorithm that you probably would have heard of while doing a course on data structures, because that's more of a data management algorithm where you manage the data in such a way that their retrieval and their sorting and their insertion is pretty optimized. Over here, we are trying to figure out something statistically. So all the algorithms that we run, they are statistically proven. In fact, they come up from the branch of statistics called as statistical learning. Then visualization. Well, of course, whatever we do, we need to present it in such a fashion that it makes sense. So with data sciences, we go beyond the basic visualization that we've seen in the BI industry with tools like ClickView and Tableau. We do have advanced visualizations, but in statistics, when you work on something which grows beyond realm of 2-dimension or 3-dimension, that is where you need something like more advanced visualization that you can do in R, and there are some libraries like D3. And finally, which is again a very important part, is called the domain expertise. So you need to know the domain. For example, I'm a data scientist and I work majorly with the life sciences data. So I'm also an epidemiologist. So I have to deal with columns with data set with with more than 10,000 columns or 20,000 columns, and that becomes really difficult for me because running a analytical model with 20,000 columns is virtually impossible. So I need to have some domain experience to figure out what could be more useful in this entire data set, right? So let's move ahead. So components of data science again. So R is programming language. What possibly could R do here? R is a programming language? Well, the answer is yes. Is it similar to Java? The answer is again a yes, because it is OOPS. It could be used as an OOPS language. But is it meant for the same purpose as Java? The answer is a big no. So we don't build we don't build any of these scripts or programs in R just to serve a purpose of an application development. Rather, most of the stuff that we do here is for statistical modeling. So R is also called as the statistical modeling language. Then this small picture that you see is of an R Studio screen where you can write a scripts and execute them in a console, which is the bottom left of this image. On the right bottom, you see a plot. So basically, R allows us to run all these kind of plots. They look really difficult at times, and they difficult in the sense they are hard to comprehend, but they are really meaningful. And all these plots can be pretty easily generated in R. Well, data science demand supply gap. Now, why the hell should we think of switching our careers to data science and big data and all that stuff? Well, I don't know if you've been to Gartner. I've been to Gartner like thrice, specifically for BI and for big data. And data science is one skill that Gartner consistently advocates on. And that's because industries are now figuring out that they've got data and they can do something really important with that data. So what exactly is that a data scientist would do? Well, a data scientist can channelize your not usable data or unused data into something which is really meaningful. So think of a scenario where you got data about your parking in particular mall. Let's say you got data about which car was parked at what time slot and when, and what was the car type and all that information about the car. Can that be used by a store that is built in that same mall, a retail store, a retail outlet of, let's say, Walmart, to predict what is the amount of ice cream bricks I need to store in my refrigerators based on the information that I get from the parking lot? Well, of course, they had that information, but with data science now, they can find correlations that can help them understand or come out with a number that will ensure that they don't fall short of these ice cream bricks. Well, in the current scenario, the industry currently is in a big need of data scientists, which could be, in fact, and all these versions that you see, big data visualizer, big data research analyst, big data engineers, architect, and analyst, whatever, all these guys are actually one or the other form of data scientists. And a data scientist is supposed to be actually a combination of all of them. So you need to know Hadoop, you need to know big data, you need to know NoSQL or a columnar database like MongoDB or Edgebase, which is more columnar. Then you also need to know the statistical part of it, which is, I think, the most difficult part. The algorithms, the data preparation, the data visualizations, all that would constitute, the work or the skill set of a data scientist. And as you see, currently only less than 1/3 are the vacancies that have been filled, and companies are ready to pay higher salaries just because this is a very rare skill. And this is not about learning yet another technology. With data science, you need to master some of the math, you need to master some of the linear algebra, you need to master matrices, you need to master machine learning, you need to master programming. Then there is Hadoop, and then there is Spark, and so on and so forth. So Hadoop and R together. So with R, there's a problem of RAM. So R basically is in memory. That means it fits everything in the memory and then runs. So if the data set is not small enough, or it's really big that you cannot fit in your RAM, then you need something like a R and a Hadoop combination where you can run different forks or different threads of the same R processes on different machines. That is provided by a technology called as Revolution in Analytics. Revolution Analytics, by the way, was bought by Microsoft in the very starting of this year. Revolution Analytics has done nothing but they've combined R and Hadoop using a package called R Hadoop, which is a combination of RMR, RHDFS, and RHBase. RHBase is something we need not to worry about right now, but RMR and RHDFS are the ones that allows us to read from a HDFS, which is the Hadoop distributed file system, and run our program in parallel on all the machines. Obviously, there are limitations to it because the algorithms like neural network or algorithm like regression, linear regression, that can't be done, that can't be made to run in parallel. So think of a Fibonacci series. So that starts with 1, then 1 again, then 3, and then 2, then 3, then 5, then 8, and 13, and so on. So basically, it sums up the last 2 numbers and comes up with a new one, and then it sums up the new one and the second last one, and then comes up with a new one. So basically, we don't have the option. So we don't have the option of running it into parallel because the final step or the output step is based on the first step, right? So that's one big challenge with parallelization. So not everything can be parallelized, but there are certain algorithms that can be made to run in parallel, like support vector machines and random forest. So we can use them in this concept called R Hadoop, and thus minimize the execution time. Well, now machine learning. In machine learning, we actually don't go beyond the data life cycle that we've seen. The only difference is that we start is with a different data set. So basically, we have an initial data set on which we run and train our models. So this is called as a training data set. So whatever is in a training data set, the algorithm will understand it. So for example, if you provide wrong data, it will give you wrong answers. So think of it in this way, that you have a image of a duck, and you tell the computer or the algorithm that it's a dog. So the algorithm will figure out these are the particular features of this image, which is now framed as dog. So next time when you show it the algorithm the image of a duck, it will call it a dog. Okay, so garbage goes in, then garbage will come out. Okay, so that's called as the training data set. So we run our problems, or run our algorithms rather, on the training data set. Now we have got a validation data set for which we know the answers again, but we ask the model to predict the values for us. And based on that, we get our predictions accuracy. Now once we do that, we run it on another data set called as a test data set or a pre-mount data set. So the purpose of this data set is to keep it totally independent from the developer who actually created those algorithms and that model, and run it in a production environment or a UAT environment where the developer does not have access to any of the test scenarios. So machine learning focuses on the development of computer programs that can teach themselves to grow and change when exposed to new data. Machine learning basically has two components. One is supervised learning and the other is unsupervised learning. So what is supervised learning? I mean, I don't want to actually go through this paragraph, but think of a case where the problem is you have to figure out whether a particular bank account will turn into a NPA or not. Okay, that's the problem. So first you need a data set that tells you that these are 10,000 records and all of them were NPAs, and these were the next 10,000 records and these were not NPAs. So the algorithm then figures out based on the label, which is NPA or not NPA, that this kind of a feature, when used in this particular fashion, converts into a NPA and vice versa. But let's say you don't know the actual labels. Well, that's when you don't have the Y, and that's a form of clustering. So majorly what we do in unsupervised learning is clustering or dimensionality reduction. We'll see it once we get into the lab. Well, the common machine learning algorithms. So basically we've got two categories. One is supervised and unsupervised. That's what you're learning. Then there is one called as regression. Then there is one called as classification. Then there's one particular step which is called as clustering and dimensionality reduction. And the final is called this. And the final there's some more categorical unsupervised learning algorithms which are called as association analysis. Basically figuring out if X is bought, then what are the chances of buying Y? So basically in supervised learning, we do regression and classification. So regression is figuring out what is the numerical value of a problem. So let's say there's a prediction analysis and you figure out what is the salary of a person. Okay. Now that's a number that you have to come up with. It's not high or low. It's not 1 or 0. So that's not classifying into anything. So basically, when you predict a numerical value, it becomes a regression problem. Of course, the way to approach a regression problem is different than way to approach a classification problem. Now, of course, regression could be linear regression. It could be polynomial regression. We'll see that. Then decision trees, a random forest. Well, these are state-of-the-art algorithms. Classification is when you want to classify a particular record into categories. NPA, not NPA is a classification algorithm. Accept the offer, not accept the offer is a classification algorithm. Good, bad, high, low. All these are examples of classification algorithms where you want to categorize a particular record, a particular document, a particular entity into one type or the other. Then in the unsupervised, we've got clustering and dimensionality reduction. So clustering is basically figuring out the clusters within the data set. So let's say you develop algorithm, develop a way to figure out what are the salary standards of a particular country. So let's say you want to divide the entire population into high or low, but you don't know whether a particular salary is high or low. So what you do is you divide the entire population into two clusters. So one cluster is for the high income and the second cluster is for the low income. And finally, we come to association analysis and the hidden Markov models. Well, these are algorithms based on the market basket analysis and if one then two kind of a concepts. Okay, so now we'll come to the logistic regression. So in statistics, logistic regression or logit regression or logit model is a direct probability model. So I believe that all of you understand what is linear regression. In case you don't, so let me tell you that a linear regression is the one which has this form: y equals to a plus b x. So y equals to a plus bx is the standard equation for linear regression classifier. Linear regression model. So what is x? X is your independent variable and y is your dependent variable. So x could be a value, it could be a variable, it could be a matrix or a vector. What is b? B is the coefficient. So y equals to a plus bx is actually the equation of a straight line in a 2D geometry. So a is the intercept and b is the slope of that line. So basically we determine slopes using concept called as least squares, and that is how we figure out the optimum value of y by fitting a curve, a straight line, in a linear regression. In logistic regression, we use the same concept, but we apply a sigmoid function, a function whose value is f of x is equals to, I'm sorry, I'm writing through my mouse pad and my Mac, it's not that great, 1 upon 1 plus e power minus x. So if you, now x in this case is our y, so f of y is equals to 1 upon 1 plus e power minus y, and that is nothing but y is equals to a plus bx. So we'll get 1 upon 1 plus e power minus of a plus bx. That will come down, and finally we'll get p of x, which we define as the probability of a particular event as e upon e power a plus bx upon 1 plus e power a plus bx. So after some calculation, you'll get px upon 1 minus px is e power a plus bx. So the quantity px upon 1 minus px is called the odds of an event, and can take on values between 0 and infinity. That's because it's raised to the power e plus e upon e power a plus bx. Well, values of the odds close to 0 and infinity indicate very low and very high probabilities respectively for an event. So let's say if you get the value of odd as 9,865, which is not a small number, we'll say the value of the probability of that event is very high. Whereas if we get the value which is like 0.84, then you'll say the value of the probability of that event is very low. So when you solve this equation again, you get, you get log of px upon 1 minus px equals to a plus bx. So you see a plus bx is the equation of our linear model, and that is why this particular function is called as the logit function or the logit function or the log odds. And that's why we see that logistic regression is linear with respect to x. Well, this is the logistic regression sigmoid function. It has some very interesting features, you see. So it is, the value is close between 1 and 0, and it crosses x equals to 0 at y equals to 0.5. So when x equals to 0, y equals to 0.5. So that means if we are looking to figure out whether a particular count will be an NP or not, then we just need to see whether the value of the sigmoid function that we are getting for it, is it greater than 0.5 or not. If it is greater than 0.5, then we say that for all those values of x, the category is blah blah blah, and for the rest of them, the categories, blah blah blah. Okay, so we do run a machine learning course in Edureka, and well, these are the modules of that particular course. We do basic data manipulation through R. We do a lot of stuff in text analytics. We go through the state-of-the-art machine learning algorithms, right from random forest to naive Bayes. Finally, we go on to integrating Hadoop and R. We also learn certain set of stuff on Mahout and machine learning in Hadoop, and finally parallel processing in R. And then we've got a project. Well, that's exactly what we've been doing so far as part of the data science course in Edureka. Well, that's the end of the slides. Well, that's not the end of the session. Now we're going to go into the hands-on exercise for logistic regression. So I'm going to open up my R session. I hope you all can see my R session. Let me see if you got a question. Well, it seems like some of you got questions. So let me see how many questions you got. Okay. Okay, so I see some of you guys have the problem with the voice, but it seems that some of you are able to hear me. Okay, so we'll take the questions after the session. Okay, so let's start with R. Okay, now the problem that I'm going to solve is regarding an organization that wanted to figure out that can we predict a particular trip as risky or non-risky. Risky means whether there are chances that the trip will have an accident. Okay, so this is about a company that transports helium in big containers, and any blast nearby or even a collision with that trunk or that container can cause an even bigger explosion, an explosion that can go up to 100 meters, which is huge. So they want to ensure and they want to be extra cautious about figuring out a possibility of an accident. Okay, so we're going to use some libraries. One such library is Carrot. So, oops. So the moment I enter here, I see the output on my console. So I've entered this Carrot library, and I've entered into the Carrot library zone. I'll use plyr. I don't need spines and R part, so I can leave that. So I've got a TRIPS dataset. Let us see what is this TRIPS dataset. So we are reading from a CSV that's on my machine. So let's see what is there in the TRIPS dataset. Well, this is the TRIPS dataset. Source is the one who is actually creating the schedule. Distance is the distance of the trip is supposed to make. Cycles, like is it going to be a round cycle or is it going to be a one-way cycle? Complexity is based on the highway it's traveling on. Then cargo, is it carrying a cargo or not? How many number of stops does it have in between? What is the start? What is the month in which it's starting? What is the day of the month? What is the day of the week? For example, if someone is working on a Saturday on the last week, then the chances are high because the person is already tired working throughout the week. Start time is in seconds. Then there's experience level in number of years, in number of months. So that's into pilot experience. Pilot 2, in case you got a pilot 2, that means you've got another driver along with the main driver. Then how many number of hours did the pilot or the driver drove in the last trip? Okay. Then pilot duty hours previously. Then the distance, the route risk _1 and route risk _2. So basically, they've given a risk measure to every route, and let's say if there are 2 routes to reach to a particular destination, then this could be then root risk is the one for the first root, and the second one is for the second root. Whether is it good or bad is like coded into 1 and 0. Visibility is taken into a numerical factor. They have quantified it using a number, but is it a good or a bad visibility on that day? Then we've got events like acceleration count, deceleration count, speed count, stability count, event count. So if we have any of these values equal to 1 or more, then we define the trip as risky. Now clearly this is a supervised learning algorithm, okay, because we already have the risk involved marked as yes or no. So let's go ahead. So first of all, I create a matrix, star matrix. So I just chose the column that I need for my for this prediction. I am now creating clusters using an algorithm called k-means cluster. Right now, in this way I've scaled my data set. Scaling the data set means normalizing the data set. So basically, you deduct the standard deviation and you divide by, you deduct the mean and you divide by the standard deviation. Then you create 10 clusters using an algorithm called k-means. With this, you find the centers of those clusters. Now you find the results of those centers into a column called results, and then you find the distance of each point from the center, and then you find out which are the most distant points which we can point as outliers. So I've chosen 1 to 1000, which are the outliers. Guys, in case if you feel like this is not making much of a sense, it's fine, because if you're not from our background, if you're not worked on any machine learning algorithm so far, it's going to look like French. But my idea is to show you how we run things and how practically, or how how hands-on are we with respect to our course. Okay. Then we convert the trips column, the trips data set into factors. Factor is nothing but any variable which has a value other than number. So let's say a gender, male, female, the height, lower high, could be the variables which we can call as factors. So now I'm running something called as a principal component analysis, which is reducing the number of variables. So we've got 23 columns, but we can use only the first 13 to figure out those which gives us accuracy of 0.94 to figure out further predictions. So that's the beauty of principal component analysis. Of course, we need not to go into the depths of it. See, I did say that we are running a supervised learning algorithm, but I've used two concepts which are non-supervised or unsupervised, which is principal components and clustering. Okay. So I create a data frame with those principal components, and now I create something called as the case and the control data set. So the problem with accidents, or problem with certain machine learning problems, are that the required events are pretty less. So think of figuring out whether a particular person will have cancer or not. So we need data sets with people who've had cancer and data sets with people who did not have cancer. So cancer is pretty common nowadays, but think of it as a very rare disease, and think of it as like 1 in 100 kind of a disease. So basically you'll have 100 people and only one guy who's have cancer. Or let's say you think about the click-through rate. So basically you are shown an ad. Now I need to figure out the probability that whether you click on this ad or not. So to do that, you need to first figure out the features of those guys who clicked on the ad. Now the ratio is 1 in 1000. So in 1000 folks, only one would click on the ad. So basically the number of actual cases are pretty less. So what we do is we do a sampling strategy called as we run a sampling strategy called as a case control sampling strategy. So in this one, we take all the data where we did find a risky data set, and we take a part of the data where we find non-risky data sets, okay, such that the ratio is not more than 1:5. Now we create a training data set like this, and now we create a testing data set. So basically the trip data set that we used, we divided into two parts. One was a training data set, the other was a testing data set. So we'll run our model on the training data set, which is the generalized linear model. And when I say family equals to binomial, it runs a logistic regression. And I'm using data equals to train my model. And here is the name of the model. So name of the model is MODEL. Pretty fast, right? Now let's make some predictions. When I say type equals response, it's going to give me the probability. So let's see, what does it give me? Pred. So it gives me some numbers, 0.17, 161, blah, 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 blah. So basically what it has given me is set of probabilities, okay, for a particular event. But what probabilities? So when I say 0.17, that means probability for an event is 0.17, and the probability for probability for one class is 0.17. So the probability of another class is 0.83. But see which probability is 0.17 corresponding to, using this function called contrast. So it says for risky, the probability is 0. Sorry, for non-risky the probability is 0, and for risky the probability is 1. So that means risky is the higher side and non-risky is like on the lower side. So what I've taken is, I've taken the threshold as greater than 0.19. So in cases where the probability value was greater than 0.19, I've marked those trips as risky, and anything greater than 0.19, sorry, less than 0.19, I've marked those as non-risky. So how did I get this numbers called 0.19? So basically, I knew that the ratio of my actual risky records divided by my total records was somewhere around 0.19. Okay. Now we create a confusion matrix to see what was my final prediction. Okay. Well, I get something like this. So 67509 are the records which the algorithm said were non-risky, and they were actually non-risky. 889 were the records which the algorithm said were non-risky, but they were actually risky. Then 30471 are the records which the algorithm said they are risky, but they are not risky. And finally, 747 are the number of events that were risky, and the algorithm also figured out that they were risky. Okay, so that's interesting, isn't it? Because our accuracy is like the total number of risky trips were 889 plus 747, and the total accuracy isn't that great, right? Let's see what's the accuracy is. So, and figure out the accuracy, which is 747 divided by 747 and 849, which is somewhere around 1327 or 1537. So let's mark it a 1540. Oops, so let me do it again. 747 divided by 1540, and we get an accuracy of around 0.48. So is that a good accuracy? Well, that's a mighty good accuracy if you look at it, because if you call certain trips that were not risky, but you call them risky, that's fine, because then you can take extra measures. But it's important that you are able to actually predict 50% or somewhere near to 50% of the trips that are actually risky, and you should be able to mark them as risky. So that's a pretty lenient or pretty acceptable accuracy rate. And let's see the summary of the model. Summary of the model is, it used 13 columns from PC1 to PC13, and these are coefficients. So these are nothing but the coefficients that we saw here. So these are those coefficients. A plus bx. So A is the intercept, which is this, and B are these different variables. So it's like minus 1.5461 plus 0.006 minus 0.006 into x1 minus 0.029 into PC2 minus 0.025 into PC3 minus 0.0167 into PC4, and so on. And that's how you construct your model. Okay, fine then. So let's start with some questions, and you all can put up your questions now, and let me see if I can answer those questions right now. Okay, so there are mighty I mean, there are plenty of questions that you guys have already asked. So what is KNN? KNN is your K nearest neighbors. Well, I've not used it. KNN basically figures out how are your neighbors doing. So for example, you've got a algorithm, you need to figure out whether a particular person is an NP or not. You find the records that are nearest to that record, and you try to see that what is the output for those records. Then another question is, what is the advantage of using R against Mahout? Well, R is basically the statistical modeling language. Mahout is running a statistical algorithm in parallel on Hadoop. Okay, so well, there are advantages of running R. So R can run most of the algorithms. Mahout is still building up. It does not have the advantage or the capability of running all those algorithms. I want to apply SVM for machine learning. So do R? Yes, of course. You can apply SVM using a package called E1071. There's another package called KernLab that you can use to run SVM. We don't need to learn Hadoop Spark for a data scientist. Well, it's not mandatory. I mean, it's not the primary skill set, but it's now turning out to be a very important skill set. So the answer is that first master your statistics, and then you go for Hadoop and Spark. How do you decide the threshold is 0.19? Well, accuracy of 0.19. The threshold of 0.19 was based on the number of records that were there in the training data set, which was like, so I had around 19,000 records which were risky, and rest of them were not risky. How do you determine which attributes to include in a prediction? So that's a very good question, Anand. There's no direct answer to it. Okay, there are multiple ways. So PC1 is one, the principal components that I used. There are multiple other ways. When you find the correlations, you find which particular set of columns are more helpful, and the algorithms to do that. So it's one of the most important aspect of machine learning, and this actually is the one that makes Omar your entire model. Why do we normalize the data? So we normalize the data because in k-means clustering, we figure out the distance between two records. So basically, if let's say the features are salary of a person and age of a person, okay, so let's say salary of a person is 10,000 and age of a person is 20, and there's another person with age as 20,000 and salary as salary is 20,000 and age as 22. So the distance between these two guys are huge, because when you find the distance, that's 20,000 minus 1,000 whole square plus 22 minus 20 whole square under root. So basically your age does not help in the distance. It's majorly the salary which is figuring out the distance. So you need to normalize your data set so that each column has a value, has a proposition to make in the final model. When to choose logistic regression? In which language the machine learning algorithms are written? So see, in R, the algorithms are mostly written in R only, but the underlying language is C++. Well, there are certain libraries that work with Java. There are certain that work with C++, but I majorly use R and Python. So R and Python are the most widely used languages for machine learning. When to choose logistic regression means in which case I should. Okay, let me just read it completely. Okay, so when to choose logistic regression means in which case I should choose logistic regression prediction. I have others method like random forest. See, there is no direct answer to it again. Okay, there are certain properties of a logistic regression which makes it better than random forest. So logistic regression based on maximum likelihood, whereas random forest is based on the vote, based on the decision trees. Okay, so it's actually question. It's basically a question when you, if let's say if you can do things well with a linear regression or a linear classifier, then I would go for a logistic regression. But if things my data is linearly not separable, then I would want to go for random forest or SVM or any ensemble. How can you say accuracy is less than 0.5 is pretty good accuracy? So it's effectively, if you see Deep, right? No, that's Lakshman. So Lakshman, if you see that the algorithm, wait, if you see my accuracy actually is not 0.45, it's actually the specificity. Okay, so specificity is like 0.45. Okay, so someone is raising a hand, so what do I do? Okay, let me go back to the questions. So the accuracy is 0.45 or 0.46, whatever. That means out of all the ones that were risky, 0.45 is 45%. With 45% accuracy, I was able to figure out the risky trips. My overall accuracy is 0.68. Okay, it is just the specific accuracy or the specificity, as we call it, which means if let's say if I was running a random classifier. Okay, so a random classifier will give me a very low accuracy. My specificity. My accuracy would probably go up. Maybe it would be 70 or 80%. Or let's say I call everything as non-risky. If I call everything as non-risky, I am bound to have accuracy of 80%, but my specificity would be 0. Okay. Okay. So my specificity is something that I want to bank on. I want to ensure that I do a good job as compared to a random classifier. So a random classifier here will not go beyond 5%. Okay. Of course, if you solve these kinds of problems more, you'll understand why and where the accuracy beyond 0.5 or somewhere close to 0.5 is really good, because that's specificity and that's not accuracy. So let's say you got a person on our web page and you want to figure out whether this person is going to click on my ad or not. Now I already know that out of 1,000 only one click on it, so I call this guy also as not clicking, and let's say there were 10,000 other guys and I called all of them as not going to click on my ad. So out of this 10,000, expected is like 100 people will actually click, or 10 people will click on my ad. But since I called every one of them as someone who's not going to visit my ad, then I also accurately classified 9,990 guys because they were not clicking. So my accuracy is 99.9. But that's not what I'm looking at. I want to figure out of those 10, how many can I accurately figure out? And if I can accurately figure out 4, then I'm done. Or 5 or 6, whatever, then I'm not doing bad. Okay. How can you say, okay, how to choose best classifier, because we've got plenty. I think I've already answered that. You need to see the data set, your data behavior. Can I have 2 decision attributes? I don't understand this question, but I think you meant, can we have more than 2 decision attributes? Can we have more than, more than 2 classes? The answer is yes, absolutely. We can have more than 2 classes. How this algorithm can help us predict the accuracy while we trade? What is that? Trade. Basically, I use regression model to find out the possible higher and minimum level of any stock, but most of the time it's go beyond those levels, which are got through regression models. Obviously, so see, it's not that easy. So you need to find either the most complex of the algorithms, and that's why the algorithmic trading guys are paid really high, and to get to the accuracy where you figure out the possible higher and the minimum value of a stock, it's not going to be easy, because if you could do that, you'll be a millionaire, right? So the answer is yes, the algorithm can help, but how it exactly can help? Well, there are thousands of things that actually constitute that entire model and not just the algorithm. We should know Hadoop or Spark for data scientist. I think I already answered that question. Any more questions? We'll wait for another couple of minutes and then we'll close off this webinar. Questions, anyone? So, Gnaneshwar Rao, I've already answered this question. No, you need to learn in case, so the question is that do we need to learn Hadoop or Spark? See, it's not the primary skill again. It's the second set of skills that you need to acquire, but do we need to? The answer is yes, we need to eventually. Not on the face of it. The primary skill set of a data scientist, one, as I've already mentioned, is statistics. You need to know statistics. You need to know the math behind the algorithms, because if you don't know the math, then you'll not be able to model those algorithms accurately, because some algorithm do specifically good with specific kind of data sets for specific kind of problems. So that is statistics. Second is either R or Python. I would say you go for both R and Python. That has to be the eventual goal, but you can start with one of them. Third is Hadoop and Spark and all that for parallel processing. And then you should also have a good creative or a understanding of the visualization part. You can learn D3 or you can do it in R also. There's another question, which is R better or SAS? I cannot answer that question, because SAS, if I say R, SAS is going to, SAS is going to hit on me. But R is open source. It's pretty handy and it's pretty cheap, even with the corporate version. And it has got, and you can do the most complex, you can run the most complex algorithm also in R. In SAS, you can still do that, but SAS is now confined to industry analytics and doesn't go beyond linear regression or GLMs. I've not used random forest ever in SAS. How good we should be in linear regression? It's like how good we should be in grammar if you want to speak English. Linear regression is a must because it's simple, and because it's simple, it does not mean it's not required. Because it's simple, I would say it's really important, because that helps you understand the rest of the algorithms. Plus, the first step where I solve any problem is actually put up a linear regression on that data. So guys, we are done with the webinar. Thank you so much for joining in. I hope this was informative and helpful for you guys. Thank you so much for joining. Bye-bye.